Pick up our notes with a discussion on what matter is. Matter is anything that has mass and takes up space. Mass is simply a measure of how much matter a substance has, and space is defined as volume. You maybe heard about volume before, maybe length times width times height, but really it's anything that has any amount of space that it takes up. Mass, typically we're going to measure in units. Something normally sized is either in grams or in kilograms. For very, very small substances, we measure the amount of matter in something like milligrams. Or very, very large, we might measure in megagrams. Mass is different from weight in that mass, because it defines how much matter is present, cannot change nor does it change from place to place, whereas weight is the measure of how much mass is impacted by gravity. So on the moon, which has 1/6 the size of the Earth, you would have a weight of 1/6 what you are here on Earth. So for example, if I weigh 240 pounds here on Earth, on the moon I would be 1/6 that, or I'd be 40 pounds. A great weight loss program. Now when we're talking about matter, we have to talk about the particles that make up that matter. Now at the most simple level, the most basic level, we have the atom. Atoms are the fundamental building block of chemistry, in much the same way that you think about the cell as being the building block of biology. When we're talking about a substance that's made up entirely of one type of atom, we are talking about the element. There are 92 naturally occurring elements, and as of late, we're discovering more and more, and we're trying to complete the periodic table, but all the elements that we do know of are located on that periodic table. When we have multiple types of atoms chemically bonded together, which we'll talk about chemically bonding later, it can form two different substances, a compound or a molecule, depending on how the substance is brought together. Another way that we define matter is the state in which we find it. Now, the state of matter has everything to do with the movement of the particles that make up your substance. Under normal conditions, we get three naturally occurring states of matter: solid, liquid, and gas. Under certain created conditions here on Earth, we can find extremely hot and extremely cold. We'll go into depth about each one as we continue here. But for the most part, all substances on Earth can be solid, liquid, or gas. Solids are very, very regimented. They have a definite shape and a definite volume. Which means that they will retain their structure no matter which environment you put them into. The particles are very, very tightly bound to one another. Think about a situation in which you're maintaining one specific spot and all you can do is move side to side. Maybe you got into trouble and your mom said, "I do not want to see you leave that spot." And you swing your arms and you kick your feet, but you never leave that spot. That's a solid. Very, very tightly packed. Another thing to keep in mind, it is not compressible. What would happen if you were to compress a solid? Food for thought. We'll talk about this in class some more. A liquid, on the other hand, has less structure. It has less structure and is allowed to flow. It has flow. The individual particles that make up a liquid sample are allowed to move past one another. They're allowed to move over one another and under one another, and they're always in this constant motion. They're not as tightly packed, meaning that they're further apart. Liquids have a constant volume, but not a constant shape. What would happen to a liquid if you were to try to compress it? Hopefully you guessed, if you try to compress a liquid, it'll actually move away. Gases are the highest temperature or contain the most energy of the three naturally occurring states of matter. A gas sample will completely take the shape and volume of its container. So it takes the shape and volume of its container. Most people think about a container as something maybe like a coffee cup or a water bottle, but in reality a container is anything that holds something else. So as you sit around the room that you're in while you're listening to this lecture, your room itself is a container for that air. We could take that same amount of air and put it into a tank. And in fact, this is exactly what we do when we go through scuba diving and that type of thing. Now, when we're talking about a gas, it's important to note that the particles are very, very far apart. They have a great distance between them. Another key term, go back a moment. Because of that great distance between the particles, they are easily compressed. That is very important for us. Otherwise, stuff like scuba gear wouldn't be very useful. Think about just how many gulps of air you could possibly get out of a tank if you could not compress that gas. Now, another major term that comes up when we're talking about a gas, one that's almost used synonymously, is vapor. Vapor and gas are different from one another. A vapor is defined as the gaseous state of a substance that is naturally a solid or liquid at room temperature, with room temperature being 25 degrees Celsius, which is approximately 76 to 77 degrees Fahrenheit. So, something that's naturally a gas, such as oxygen or nitrogen or hydrogen, would not be considered a vapor at any point. Something like carbon, though, would be. Carbon is a solid at room temperature, and if you were to heat it hot enough to turn carbon into a gas, that would be considered carbon vapor. At the extreme ends of our states of matter grid, we have two very, very, very different substances. The state of matter at the extreme hot end of the scale is a plasma. Think about plasma as being a gas. I always grew up thinking about plasma being more like electricity and that kind of thing, but it's very, very different than that. A gas is moving around very, very fast. And if you keep giving it more and more energy, which causes that heat to increase, eventually what happens is the electrons that are made up in that gas actually escape from the particles themselves and start to free flow. This gives a plasma a charge. So you can think about a plasma for now as a charged gas. On the opposite end of our spectrum, we have the very, 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 very cold. Now, as I mentioned before, particles are always moving around. In a solid, they're very much only vibrational. They can only move side to side, up and down, but they can't flow past one another. And as you go from a solid to a liquid to a gas, we increase that amount of flow. In a Bose-Einstein condensate, all energy has been removed. And so there is no side to side anymore. It's an extreme cold temperature. And at that extreme cold temperature, all the atoms begin to overlap and form this giant atom, this superatom. And that superatom is what we see in this picture right here. As these individual particles begin to slow down and get closer and closer, they begin to form a pile right here. And as you continue to get closer and closer to this thing called absolute zero, which is approximately negative 273 degrees Celsius, they begin to pile up. Much like if you keep adding sugar to a sweet tea mixture, it'll start to pile up at the bottom of your pitcher. And what you get here is an overlapping of all these atoms into this one big superatom called a Bose-Einstein condensate, where very, very strange things happen. We'll talk more about this later. So in summary, there really are 5 states of matter. The 5 states of matter include the ones that you've already known about: solid, liquid, and gas. but also include a couple newcomers to the party, a plasma and a Bose-Einstein condensate. For discussion tomorrow in class, you should have any questions made readily available to me about the states of matter and the individual movement of the particles. You should also be able to rank them according to their energies. You should know which one has the highest amount of energy. And you should be able to easily recognize simple definitions of a solid, liquid, and gas, such as non-compressible, always has the same structure, that type of thing.